Good morning, class. This is ECE 2002, start of week 6. Hard to believe it, but after the exam this week, there'll just be 7 more lectures. So as of today, that means we have 12 lectures left. So it's the time to really solidify our knowledge of linear circuits and electronics, and make sure we're prepared for our 300 level classes. For many of you, this is the last of your 200 level classes. Riyadh was making coffee. Yeah, you missed the part where I said, yeah, we're going to have tons of graphical convolution coming up. Maybe not, though. Before we get started with the new lecture set, let's take a quick poll of the room and see, do we have any questions about homework 5, quiz 4 that we just took, or anything related to exam preparation? Is everyone feeling comfortable with the upcoming exam? Ready to take it tomorrow? Not quite that confident? Not exactly. Convolutions. Yeah. So would someone like to say they would like to see a convolution problem in the exam 2 review sessions we'll do later this week? Okay. We'll see. We'll see if I can get a good convolution problem written without giving away anything on the exam. AJ says Bodie plot presentation. Yeah, I realized I should have given, I normally give people a step-by-step procedure in the slides where it's just like, step 1, do this, step 2. I gave rules, but I never really gave a procedure for Bodie plots. So we'll see if I can do the Bodie plots too. If I forget, which I probably will, this is a good use of Piazza, is be like, I want to see more of these types of problems. So someone can make a Piazza post. We could have a bunch of discussions of, I want to see a convolution problem. I want to see inverse Laplace transform with, repeated imaginary roots. I want to see something else. I will add to the slides. I'll do what I did for exam 1, where I create like a brief little solution manual in LaTeX, and it's like a regular document where it works out a problem. Well, the lecture is available on Brightspace, unless there is some sort of error I didn't know about. But the lecture on Friday covered the remainder of lecture set 5, which is on using resonant circuits as bandpass filters. So it introduced a bunch of terminology. Some of that terminology we get to use today. When you denote multiplicity of poles and zeros, I just off to the side on a pole 0 plot, you would just put like a 2 or a 3 like in the upper right corner of the polar 0 symbol. So X for poles, O for zeros. Yep. Just like they say in the Ellie song, where it's like X's and O's. When you denote multiplicity, put the number in the upper right-hand corner. Or maybe I'm misremembering the lyrics. Any more questions? Definitely good things to mention from the class. Seeing none, I'll go ahead and share my screen. And now we'll start a brand new lecture set 6. So it's frequency response of FET amplifiers. So this covers chapters 30 and 31 in the Slavich and Turlet book. I keep getting questions about what are the relevant chapters, for the exams. Well, the lecture sets tell you what chapters are covered. So, and like each topic on the topic slide tells you, this is the outline slide. It tells you basically what, each topic corresponds to a chapter. So this is chapter 30. The second one is chapter 31, in case you haven't caught on to that. So everyone's favorite thing from the first part of the class, single transistor amplifiers, come back with a vengeance. So we need to, brush up on all of that stuff if we need to, so that we can talk a little bit about the frequency response aspects of amplifiers. Those who thought they could just forget this stuff, they were sorely mistaken. It comes back, and this will be on the final exam. So the first thing we'll talk is about the low frequency response. And the second thing we talk about is the high frequency response. And the middle frequency we already covered. So that's great. So whenever we said middle frequency amplifier gain, that was what we already covered. And mid frequency, input impedance is just, input resistance, so on and so forth. So we'll say external capacitors control the low frequency response. And we'll talk about the method of short circuit time constants, or SCTC. And then we'll get into a high frequency transistor model. Internal capacitors control the high frequency response, and Miller theorem and method of open circuit time constants. So some analysis techniques. So despite being 2 lecture slides, I had a lot of material prepared. So, or 2 lecture chapters, I managed to stretch it out into 49 slides. So lots of information, just like in lecture set 1. Please, please, please slow me down if I'm going too fast, because I've been teaching this for a while, so I sometimes forget what are the challenging aspects to get. So the first thing is, we talked about amplifier gain. We denoted it with like A sub V or G sub V, which was amplifier gain of the voltage gain of the amplifier proper, or overall voltage gain. And we're going to learn that that is really a function of frequency, as we expect. We wouldn't expect the gain to be flat for all frequencies, forever. So capacitively coupled amplifiers, which are the ones we were building with discrete components, like, MOSFETs that with 3 leads that would stick into a breadboard, they're going to fall off with decreasing frequency. So as the frequency gets really low, the gain falls off. Directly coupled amplifiers, like the ones that are built, from scratch on, a silicon die by VLSI engineers, they're going to have their midband extend down to DC, hence the name directly coupled DC. Good mnemonic right there. So they don't really experience a low frequency loss of gain. So all amplifiers will experience gain changes at high frequencies, though, because of capacitive effects within the transistors. So bandwidth is an important amplifier design metric we have skipped until now. So we already talked about mid-band gain, input resistance, and output resistance. And, we were able to get by with simpler low-frequency small signal transistor models. You remember the hybrid pi model and the equivalent T models? Well, those were our, quote-unquote low-frequency small signal transistor models. They also work at middle frequencies too, but, they're just lower than, say, hundreds of megahertz or gigahertz range models. So we're going to have to update our hybrid pi and equivalent T models to capacitances to model frequency-dependent behavior. So this lecture set is going to teach 2 different skills. So it's going to, do some case studies for the frequency response of amplifier configuration studied so far. People wanted more examples in the first lecture set. Again, that's somewhat hard to incorporate, because if I show you exact calculations for, 3 different amplifier configurations, common source, common drain, and common gate, there's, all I can do is just, change the external resistances or capacitances. I can't really do too many other examples. There's not like something new per se I can throw out at you. All you can do is just change the surrounding circuit. And then we'll also deal with principles of frequency response that apply to generic amplifiers. So let's take a look at the frequency response of like a discrete common source amplifier. So CS is common source amplifier, and here's the gain. So we talked about mid-band before, so in between FL and FH, which are our upper and lower, linear cutoff frequencies, or half power frequencies, if you remember that term from lecture set 29. So the maximum of the gain occurs in the mid-band, and it's at A sub m, for mid-band max, mid-band gain. And we see that, this logarithmic plot, log plot, in decibels and in logarithm frequency, it's very flat in the middle. So FL is probably down near 100 hertz. FH is probably up near 100 kilohertz or a megahertz. So for a common source amplifier. So that means, there's a span of, I don't know, anywhere from 4 to 5 orders of magnitude where this is really, really flat. And we call it the midband. But once we get below FL in frequency, we reach the low frequency band. And then it'll, we'll have that transition at AM minus 3 decibels, where again, minus 3 decibels occurs because 20 times the log base 10 of 1 over square root of 2 is negative 3.0102 decibels. Similarly, at the high frequency band, we get this behavior with increasing frequency, roll off of gain. And I said, if we had a directly coupled amplifier instead of a crossly coupled amplifier, this midband would just, extend kind of as a, line all the way towards 0. It would just stay flat forever. And it would look very different. But one thing is to say, this, picture I'm drawing should be very familiar. This is the magnitude response of a bandpass filter, which is exactly what we talked about in the previous lecture set. So next, amplifier frequency response. So a real transistor amplifier has finite bandwidth. So our analysis will only apply to the relatively wide flat midband. So everything we've done up until now applied to the midband where, gain was nice and flat. Hence why we calculated, we got numbers, we didn't get functions of frequency. At lower frequencies, the gain rolls off due to coupling capacitors, CC1, CC2, and the bypass capacitor, C sub S, having a larger reactance. We said they were basically infinite capacitances before. Now we can no longer say that they are basically infinite capacitances. We have to deal with the finite nature of their capacitance, leading to a large reactance at sufficiently low frequency. At higher frequencies, the gain rolls off due to internal capacitive effects of the FET, which we'll have to postpone until the next topic. So the midband boundaries are F sub L and F sub H, where the gain drops by 3 decibels from its maximum at the midband center. And then similarly, you can multiply these by 2 pi, and you can get your radial frequency, half power frequencies, omega sub L and omega sub H. This class, we like to deal with omega more than F. A lot of people think in hertz, but like we find the math is easier if we deal with radians per second. So we'll stick to radians per second. So the bandwidth, B sub omega, measures the size of the useful midband, and the gain bandwidth product, GB, is a figure of merit showing how much the midband gain and bandwidth can be traded off. So as a reminder, B sub omega, the bandwidth, omega H minus omega L. But I just said this is about, maybe 100 kilohertz, maybe a megahertz, minus something that's below 100 hertz. So 1 megahertz minus 100 hertz is 999,990 hertz, which is basically the same thing as 1 megahertz. So, and then multiply by 2 pi to make these into omegas. So we're going to deal with omega sub H, is basically equal to our bandwidth. And this gain bandwidth product basically shows you how good of a quality the amplifier is. Because you can usually say, I want to sacrifice some midband gain for bandwidth, like we did with the degenerated common source amplifier. But overall, the product usually stays fairly constant. So it's some indication of the quality of the components you're using and how smart the topology actually is. We don't calculate it very often though, because it requires a lot of work. But if we had the midband gain and the bandwidth, it's fairly easy to calculate. Just multiply the two. Hence the name gain bandwidth product. So high pass filters for low frequency effects. So low frequency effects usually involve the external capacitors in series with the primary source current flow. So say we have the Thevenin equivalent of a source, so V sub S sinusoidal source and R sub S series resistance. We normally find that the output voltage across the primary load resistor R sub P is what we're interested in, and the C sub S is in series with R sub P. This is in series with our primary source current flow. So when we find IC sub S, that it's going to be very important. So because it's in series, think of the capacitor at sufficiently low frequencies. This behaves more and more like an open circuit. So it's going to, present a higher and higher impedance as frequency goes down until we get very little current through the resistor, and thus we reach our cutoff frequency. So we call this a high pass filter characteristic. So we're introducing high pass filters for the first time formally. So yeah, usually putting the capacitor in series with things makes for a high pass filter, which means it'll control our low frequency effects. Conversely, if we have a shunt capacitor, we'll see that it creates a low pass filter that dominates high frequency effects. So for high frequency effects, we usually have internal capacitors or capacitances that are in parallel with the primary source current flow. So our primary branch of current flows around this outer loop with our Thevenin equivalent source, VS and RS, and then through our primary load resistor, R sub P, where we measure the output voltage across it. And then we have C sub P being our resistance that is in parallel with the primary load resistance, and thus it acts as a diversion for current, diverting more and more current at higher and higher frequencies. So as you go from the middle frequencies up until the upper cutoff frequency, it goes from being a very high impedance and basically an open circuit until it conducts sufficient current, and then eventually more current through the capacitor than through R sub P. And then because more current is going through the capacitor and you get very low current through R sub P, that means the voltage across R sub P decreases. So we see a roll off of our output. And this is the low pass filter characteristic. So capacitors in parallel with our load basically produce a low pass characteristic. What questions do we have? Low frequency effects, it blocks low frequency input. Yes, on slide 6. At sufficiently low frequencies, this is a large reactance. So you get most of the voltage drop across the capacitor instead of across the resistor, which means less current flowing overall through the circuit. Okay. So let's look at a motivating example. So the common source amplifier we said was the most common of our amplifier configurations. So let's look at it. So here we see that we have we switched to capital letters because we're going to deal with frequency response things. So, we're gearing up to start thinking in terms of the frequency domain. So we'll have V sig be our signal source, R sig be its, Thevenin equivalent resistance. And then we have this coupling capacitor CC1 that feeds into this resistive voltage divider by RG1 and RG2 between VDD and ground that biases the gate of the MOSFET. The source of the MOSFET has R sub S for biasing purposes, but it also has this parallel C sub S for as a bypass capacitor. And we, in the ideal case, midband frequencies, we expect V sub S right here, the source voltage, signal frequencies to be 0, but at sufficiently low frequencies, it'll be non-zero. So we have to deal with that. And then RD is part of the biasing network, and it's our load resistor too, or not load resistor, but it's also it converts our output current into an output voltage. So RD is our drain resistor, VD at the drain. We'll have a coupling capacitor CC2, then we'll have R sub L as our load resistance to ground, and we measured the voltage across it. So hopefully everyone remembers how we analyze this type of circuit. So we do our DC biasing, so we figure out, the amount of drain current that goes through this transistor, and then from the drain current, we can easily find G sub M. Remember, the FET transconductance is equal to square root of 2 kn ID. So we can get GM for our small signal models. If this has a non-zero lambda, our channel length modulation parameter, then we can also find the output voltage using I sub D, the drain current. Then step 3, which is back on slide 69 of lecture set 1, step 3 tells us that we need to start building our small signal equivalent circuit. So we turn off all of our DC voltage sources. They get replaced with short circuits to ground. DC current sources get replaced with open circuits. We don't have infinite capacitors. We have finite capacitors, so we just got to leave them in place. We don't have infinite inductances at all, so we just ignore the step where they become open circuits. And finally, we need to use a small signal model for our transistor. So we will use the equivalent T model because we are going to have impedances attached to the source. And then lo and behold, it's exactly like I said. Just take a moment to figure out how we got here. So, we just redraw things. V sig is a signal, so it stays. R sig is part of the small signal circuit, it stays. CC1 exists as is. RG1, short circuit to ground at the top. RG2, short circuit to ground. Well, it's already grounded. And then we'll use equivalent T model. So we'll have, 1I is our current source here, where the control current you have to label is right here with 1 over GM as a resistance in our small signal model. We also have the output resistance right here between drain and source. Our source has RS going to ground and CS going to ground. And then our drain resistance attaches to our drain on one end, which is up here. And then we also need a short circuit to ground where VDD used to be. CC2 we leave in place, and RL is right here. So that's how we get VO. A lot of you struggled with the small signal equivalent circuit, but by the time we get to lecture set 6, it's basically a given that you can draw them perfectly. So, definitely when it comes time for the final exam, review lecture set 1 heavily so that you can also prepare for lecture set 6. Any questions that we have so far? None? So now we have our discrete common source amplifier analysis. So the small signal equivalent circuit cannot assume zero impedance for your capacitors. These are not infinite capacitors because we're dealing with sufficiently low frequencies. So we'll use our low frequency equivalent T model. Again, that's the equivalent T model we've been using all along. It's going to work just as well because we said external capacitors control our low frequency response. The capacitors have impedance in the form Z sub C is equal to 1 over SC. Right? We know how impedance works. And we're going to neglect R sub O, the output resistance, because it just adds so much difficulty to our analysis while having a fairly minuscule effect, especially at very low frequencies. Like little R sub O is not a controlling component in this circuit. It's not a controlling element in this circuit. So we just ignore it. We'll replace it with an open circuit. So R sub O goes to infinity. So we're going to, do this very formally the first time, and then we'll learn tricks to do it, faster. Because as engineers, we need the fast way rather than the most formal way. Computers are good at being formal. Humans sometimes need approximations. So let's do this formally. So the overall voltage gain as a function of complex frequency S is defined as V sub O divided by V sub sig, which we're going to say is, VG, the gate voltage, divided by V sig, times ID, the drain current, divided by VG, times VO divided by ID. So we'll just break it up into 3 separate terms we can all multiply together, and you'll notice the VGs cancel, the IDs cancel. So this is just an expansion of what we have of VO over V sig. And to keep things somewhat tidy, we'll define RG as RG1 in parallel with RG2. Right? These are obviously resistors in parallel. And we'll say RS is in parallel with 1 over SC sub S. Because, these impedances are obviously in parallel with each other as well. So we have an input voltage divider because the input resistance looking in to the gate of the transistor is infinite. So we can just basically detach what happens here and just get the output voltage VG across these resistors. So this is an input voltage divider with 3 different impedances, R sig, CC1, and RG. We're just trying to get the voltage across RG. So we'll get RG divided by RG plus 1 over SCC1 plus R sig. Because 1 over SCC1 and R sig is itself an equivalent impedance. This is the sort of top impedance of our impedance voltage divider, and RG, which is that parallel combination of these 2 resistors, is the bottom impedance of our voltage divider. So, just like all along, we've been expecting that you're good at ECE 20001 knowledge. Here, we're dealing with so many, elements in our models. We're not going to be able to explain fully sometimes how to do the math. It's just assumed that you know how it works by this point. So we can simplify this by multiplying through by top and bottom by SCC1 and then dividing by the coefficient of S. You work that out and you get RG over RG plus R sig times S over S plus 1 over CC1 quantity RG plus R sig closed quantity. And I claim to you that this is the form of a first order high pass filter. Where that comes from, I'll get to in 2 more slides. So by Ohm's law, the current I is equal to this current here, I is equal to ID. So ID divided by VG is the same thing as, these 2 impedances, 1 over GM, and then RS parallel with CS. And right. So we look for the equivalent admittance here. where we're going to get 1 over GM plus admittance of these things, and then divide by 1, or reciprocate rather. I'm a little tongue-tied right now. So that is what we have here. So we'll get GM times quantity S plus 1 over CSRS over S plus GM plus RS to the -1, all that over CS. And I claim that this is a general first order filter. And then we have an output current divider where IO, which is the current through the load resistance, how it compares to ID. Well, that is just going to be the other impedance, which is just R sub D over R sub D plus the impedance of this branch, which is 1 over S CC2 plus RL. And then in order to get VO from IO, you just multiply by an RL. So you'll get, when you simplify things out, negative RD RL over RD plus RL times quantity S over S plus 1 over CC2 RD plus RL. And this is another first order high pass filter. That was a lot of work. We're not quite done yet. We have to multiply everything together. So we multiply this term by this term by this term. We will get GV as a function of S is defined as VO over V sig is defined as A sub M and then S over S plus omega P1 times S plus omega Z over S plus omega P2, that times S over S plus omega P3. So the low frequency gain function combines midband gain, a 0 frequency, and 3 pole frequencies. So this is all factored out so that it's easy to see, okay, we got zeros and poles. Like we said, you can always factor a rational transfer function this way. So we have a midband gain, which is A sub M equals negative RG over RG plus R sig times GM, RD in parallel with RL. Because we have a negative sign from the third factor. We have the input voltage divider right here. We get a factor GM. And then we also get this right here, which product over sum of resistances is just parallel resistances. And sure enough, if we were to go back to the exam 1 equation sheet, look up the midband gain for a discrete common source amplifier, you would find this equation. So this is exactly what we expect to get for midband gain. So the 0 occurred at 1 over CSRS. It's on the negative real axis. There's a double 0 at DC, S equals 0. It's why we call these blocking capacitors, is because we expect CC1 and CC2 to basically block what happens at low frequency. So the 0 is at DC. And then we have pole radial frequencies, omega P1, 1 over CC1, R sig plus RG, omega P2, GM plus RS inverse over CS, and omega P3, 1 over CC2 quantity RD plus RL plus quantity. Okay, this is already way too complicated to actually deal with. We should do a Bode plot with typical values, noting that we're typically are going to have omega P2 much, much bigger than omega Z. The response should be flat at the midband, A sub M, once FL approximately equal to FP2 is reached. Because we're claiming that omega P2 is the largest such pole. Before we can do that, we really need to look deeper into all the different possibilities for first order filters. So let's use our tools from the magnitude response and just see all the possible options we can get for a first order filter with a single, in other words, a filter with a single pole. So let's say we have h of s is equal to k times omega naught over s plus omega naught. Well, this is going to start at 20 times log k at an absolute value, and then it's going to roll off once it reaches omega naught with an asymptotic slope of negative 20 decibels per decade. And the exact ones in blue where it's 3 dBs down at omega naught, and then the Bode plot is the red dashed line using piecewise linear approximation. A high pass filter is something very similar. We get h of s is equal to k times s over s plus omega naught. So already we can see we have a 0 at 0 and a pole at omega naught. So because we have a 0 at 0, we're going to start with an asymptotic slope of 20 dB per decade. And then at omega naught, our piecewise linear approximation flattens out at 20 log absolute value of k for a magnitude response. And of course, at the actual cutoff frequency, omega naught, we would get 3 dB down. I guess this is a little bit different. We've been using omega naught for natural frequency. Here, omega naught is the cutoff frequency. Not natural frequency. You can't have a natural frequency with a first order circuit, but that may not be as apparent to someone who's just starting their circuit knowledge this semester, or their filter knowledge this semester. So we have the LP filter, the HP filter. Now let's look at the general filter. So the general filter has a 0 that's not at 0 and a pole somewhere else at omega naught. So the way this one is structured, a naught over k is less than omega naught. So we're going to start with a 0. We're going to start with 0 slope. And then at a naught over k, we hit our 0. So we get an asymptotic slope change of plus 20 dB per decade. And then we'll flatten out at omega naught again. So we go from 20 log k, 20 log absolute value k, a naught over omega naught. And then we flatten out again at 20 log absolute value of k. Now you can also have the general filter the other way, where you start high, slope down at negative 20 dB per decade, and then flatten out. That would be the sort of more low pass like general filter. That just means that omega naught is less than a naught over k. So and of course, here's the dashed line showing the Bode plot approximation, which, it's a little bit off where things change, quickly, but as a whole, it's not that bad of an approximation. And then we have this brown line right here where it just stays flat. So what happens if you make a naught k equal to omega naught? Well, then you have a pole and 0 overlapping. You would cancel the numerator and denominator. So you're left with h of s is equal to k. So you would just stay flat at 20 log absolute value of k. This is the all-pass filter, which is every student's favorite filter, though I'm forced to make the joke that this class is not an all-pass filter. We are a high-pass filter when it comes to grades. Have to make that joke. You can put all these things together and you get, you'll start at a 40 dB per decade slope. Then at omega z, you'll start going up at a faster 60 dB per decade slope. At omega p1, you dip down to 40 dB per decade, omega p3 to 20 dB per decade, and at omega p2, you'll flatten out exactly so that you're, asymptotically flat. So we call this omega p2 is equal to 2 pi fl, which is equal to omega l. Because for a common Bode plot, you would get something like this. Any questions about how we went from circuit to small signal circuit to a very complicated gain transfer function to simplifying the terms by factoring the numerator and denominator polynomials with the midband gain involved, and then looking at general first order filters, and then got the actual Bode plot. Aubrey's question, log notation on the right slide plot in slide 12. Log notation on the right plot in slide 12. 20 log absolute value K times A naught over omega naught is right here. And then the top one is 20 log absolute value of K. Where log is the common log raised 10. And of course, we're dealing with a logarithmic frequency axis too. Yep, it's division. K times A naught over omega naught. Any other questions? So I'll move on. So we'll talk about dominant poles in the low frequency response. So we got the Bode plot by plotting magnitude of GV of S after substituting S equals sigma plus J omega with sigma equal to 0. i.e. we're evaluating along the imaginary axis, which is, the purely sinusoidal input domain and sinusoidal output, hence sinusoidal steady state. So complex magnitude can be evaluated factor by factor. So that's why we were able to just look at, magnitude of AM. So that just, take the absolute value of this term, the modulus of S over S plus omega P1, modulus of S plus omega Z over S plus omega P2, and the modulus of the last term as well. The boundary frequency, F sub L is omega L over 2 pi, is found where GV of J omega equals magnitude of AM over square root of 2, right? Because we defined in the previous lecture, the previous lecture even, that, these boundaries occur where the maximum gain, the midband gain, falls off by square root of 2. So the Bode plot approximations work very well when poles and zeros are well separated. So yeah, as you can see, these are very separated on these, prototype first order filters. And then, here where we have the zero fairly close to the pole, we see that there's a little, significant amount of deviation, from the asymptote, but there is a small segment in the middle where it is well approximated. But when poles and zeros aren't well separated, we'll have to deal with other things. So in the case that they are, find the midband gain magnitude. You can do this by, being very formal and finding it. But however, we know how to find the midband gain magnitude for the normal circuit without having to consider finite capacitances. So we know how to do that already. We increase the asymptotic slope moving leftward over logarithmic frequency by 20 dB per decade for every pole passed. So I guess here, for every pole passed, as we move left, we'll start flat, 20 dB per decade, another 20 dB per decade, another 20 dB per decade. And then we decrease the slope moving leftward over logarithmic frequency by minus 20 dB per decade for every zero passed. So here we get plus 40 dB per decade. And this would continue all the way down forever and ever in log frequency space. These are the Bode plot rules that we developed in the previous lecture set. So a dominant pole is considered to exist if the highest frequency pole is at least a factor of 4 times, that is to say 2 octaves in engineering speak or musician speak, greater than the next closest pole or 0. So then we just say omega L is approximately equal to omega P2, where omega P2 is our dominant pole because it's at least 4 times greater than omega P3. If no dominant pole exists, then the boundary frequency is approximately this expression, omega L approximately square root of omega P1 squared plus omega P2 squared plus omega P3 squared minus 2 times omega Z squared. Or we don't have time to get into how to derive a formula like this. You just have to sort of take it as is. No time to derive. if you're really, really curious, go to lecture set J5, the imaginary lecture set that covers amplifier frequency response. So the capacitors in the common source amplifier act independently, allowing for rapid analysis. The zeros occur at S values where the input signal does not reach the output. So there's a double zero at S equals 0 DC. Each coupling capacitor blocks the signal at DC, as we would expect. There's another transmission zero where Z sub S, where we said that was RS parallel with CS, goes to infinity. So the circuits on the next slide will help find the poles quickly. So the poles exist under zero input conditions. So that's part of the natural response, not the forced response. So might as well just turn off all of our sources. So we set the DC sources to 0, analyze the circuit separately. So that means voltage sources become short circuits. So let's do this real fast. We'll go through these last two sub bullet points and then look at this. So CC1, what resistance does CC1 perceive? Well, we can move it to either side of these resistances, but it's hopefully with a little bit of thinking, you should be able to figure out that CC1 perceives RSig and RG in series. So the equivalent resistance perceived by it, is RG plus RSig. And so we could say tau1, the time constant, is just CC1 times RSig plus RG. So for this one, which is C sub S, the bypass capacitor, when we turn the source off, we basically see a short to ground at the top of 1/GM. We also see R sub S over here. So it sees this resistance and then this resistance in parallel. So we can therefore say tau sub S, the time constant associated with this capacitor, is C sub S times quantity RS in parallel with 1/GM. And then lastly, tau2, time constant associated with this capacitor is CC2 times RD plus RL, because RD and RL appear in series with this capacitor. And then we can just say each pole is just omega sub pk is equal to 1 over the time constant. So 1 over tau c tau k, with index k denoting each capacitor. So that's exactly what we have written here on slide 15. Back to slide 16. So if you're choosing to do this as a design problem, you would choose to make omega L where you want it to be while minimizing the sum of the capacitances, the smallest possible capacitors to minimize the cost in your circuit. So we want to minimize CC1 plus CS plus CC2. We typically want omega P2 with the pole associated with C sub S to be the dominant pole frequency. So that will help us achieve the minimum capacitance sum. So we might set omega P1 and omega P2 lower by a factor of less than 0.2 times this pole to ensure the dominance of omega P2, being mindful that CC1 and CC2 remain small themselves. Questions? There is no imaginary series lecture for Laplacian convolutions. You just get the normal lecture sets, because I don't have previously taught material that I could convert into imaginary lecture set. The imaginary lecture sets came from my ECE 255 talks. And I don't have previous stuff on Laplacian convolutions. Significance of omega, what's that in parentheses, AJ? Omega L? So if we go all the way back to the very start, omega L is this half power frequency where it starts the low frequency band by being 3 decibels lower than the mid band frequency. So this is important because it's one of our boundary frequencies for the mid band, and it helps define where the transition of behavior in the circuit happens. So we say omega L is basically the same as our highest pole. Any more questions? So let's talk about the method of short circuit time constants. So when the capacitors interact, it's extraordinarily difficult to find the poles. We didn't have to deal with that with the discrete common source amplifier, but like if we had, some sort of interaction where like, one capacitor could perceive the other capacitors, like, oh boy, this is, not very easy to find out. And we wouldn't be able to find out the exact, gain transfer function exactly without, driving ourselves nuts. So we'll talk about the method of short circuit time constants, or method of SCTC, to estimate the 3 dB frequency omega L without needing each pole frequency omega sub pk. So we set the input signal to 0. Then we'll consider one capacitor C sub k at a time while setting the other capacitors to infinity. So all the C sub L goes to infinity for all L not equal to k. That is, we're short circuiting all the other capacitors, hence the name short circuit time constants. So we'll just consider one capacitor. All the other capacitors get replaced with short circuits for the time being. Then we find the equivalent resistance perceived by C sub k by inspection. As we did right here, we perceive these resistances by inspection, or by using a test source V sub x and finding R sub k equal to V sub x over I sub x, where Ix is the current that would flow through that test source. And then we just repeat this for every capacitor in the circuit. And then we calculate the 3 dB frequency as omega L, approximately equal to the sum from k equals 1 to the number of capacitors of 1 over C sub k R sub k, which is just saying 1 over the time constant k. Hence the name short circuit time constants. We did that basically previously. So the method of short circuit time constants assumes there's a dominant pole, but it's still quite accurate even with general pole positions. So that's why it's an approximation going on right here. As a bonus, the method of short circuit time constants makes it possible to determine the relative contributions of each capacitor to omega L. So we can basically say, okay, this contributes 80% of the lower cutoff frequency. This contributes 10%. This contributes 10%. Because you could just look at, how much each term does to add up towards omega L in radians per second. What questions do we have? Want to see this in action? I do. So we have two other single transistor amplifier configurations we talked about: the discrete source follower, or in other words, the discrete common drain amplifier. We also have the common gate amplifier with discrete elements. So here's a discrete source follower. We have our Thevenin equivalent source, Vsig and Rsig, coupled capacitor CC1 with RG1 and RG2 between VDD and VSS. Q1 has the drain tied directly to the source voltage, and the source has it tied to RS through VSS. Then we have CC2 and RL. Output is taken across RL, our load resistance. So at low frequencies, we do our trick. So normally we would find the DC information, calculate the drain current, and then from, involves the quadratic equation, not very fun, as you did on the first exam. Then you calculate GM, and then with GM, you can also calculate RO. And then we move to the small signal equivalent circuit. The Thevenin equivalent source stays the same. Capacitor has to stay in place because it's sufficiently low frequency. This gets replaced with a short circuit to ground. This gets replaced as a resistance with a short circuit to ground. We ground the top, and we replace RS with a short circuit to ground, or resistance with a short circuit to ground. capacitor stays in place, RL stays in place, use equivalent T model. Lo and behold, we get this. Now we did the trick that we did previously, where because RO would be between this 1/GM node right here and the top, which is ground, we just physically picked up the end and reattached it to ground down below so that it was easier to do our analysis. But otherwise, this is a direct application, maybe a second draft of the small signal equivalent circuit that we would try to draw. So we can go ahead. The circuit capacitors on the CD circuit act independently, allowing for rapid analysis. The circuits on the next side will help find the poles quickly. Poles exist under zero input conditions, so we set all DC sources to zero, analyze the circuit separately. Actually, it says DC sources. We should just say set all sources to zero. That's DC and AC. All sources to zero. All sources to zero. Yeah. So we can even set all sources to zero, not just the DC ones. So let's look at the equivalent resistances. So first, let's figure out what CC1 perceives. So it's going to see the nothing happening through the gate. So you can figure out VG by looking at RG, which is RG1 in parallel with RG2, and just our sig. And then we have this source turned off, so it's just replaced with a short circuit to ground. So CC1 perceives RSig and RG. Its time constant CC1 quantity RG parallel RG2 plus RSig. Then we have CC2. It sees RL on one side to ground, R0 to ground, RS to ground, and 1/GM to ground as well, because this is sufficiently disconnected. So we have CC2 sees RL plus 1/GM parallel RO plus parallel and parallel. I'll repeat from the beginning. CC2 sees RL in series with the parallel combination 1/GM parallel RO parallel RS. And that's how we get this time constant right here. Each pole is just omega pk equals 1/tau k for each index k. So if we were doing this as a design problem, we would place omega L on minimizing the sum of capacitances CC1 and CC2. We want omega P2 to be the dominant pole frequency, so the one associated with this, coupling capacitor and the source. Make it the largest capacitance to minimize the capacitance sum. We'll set this to be lower than a factor of 2 times to be the dominant, to make sure CC1 still stays small. What questions do we have? Yeah, you will have a very bad time if you've been doing hybrid pi model only, just because everything you do would basically require you to go through this step of finding the equivalent resistance by, applying a test source and then measuring the test current. That's a lot more work, especially when the alternative is finding 2 or 3 capacitances by inspection. Yeah. Any other questions that we have? If not, I'll be doing office hours from home today. Class is dismissed. Thank you for attending. You're welcome, everyone. Bye.